Hello students, welcome to the class. So today we'll see the theory part 11 of the chapter 5 Thermodynamics. So this is the disclaimer. Now in this lecture I would be focusing on a topic which is I would say new to you. Maybe you have not heard about it. So it is basically Maxwell equations. Now not those Maxwell equations given in a physics book, but this is related to your thermodynamics. So there are certain relations for the state functions and the path functions which are given, right, which are given to describe them in a different way. Now these equations are important and a good way to score marks at the same time. If you know the equation, and then you can easily choose your correct option, and that's all for that you can say given equation. Okay, you don't have to go into the derivation part, you don't have to know that how it is coming. There are certain tricks and certain relations. I will tell you those tricks, and I guess you would grasp them in an easy way. So it's very easy to understand those tricks, and after that, you will be able to learn a large amount of relations which you can use in your numericals as well. Okay, so with this, let us start. Now, to know this Maxwell equations, we have a Maxwell square. So you call it as magic square also. So there are certain names given to this. You can call it as magic square, Bond square, or thermodynamic square, right? So these are all names given to this Maxwell square, which is there to create a easy way to learn the relations of Maxwell. Now, this will help you to recall and derive these various thermodynamic relations. What is that square? So this square is Maxwell square. You can see that we have certain terms which are given on the corners as well on the middle, right? So we have S, H, P, G, T, A, V, U. There is a very short trick to learn this. So what is the short trick? So the mnemonic that is used is for the corner terms, if I say, so it is Satya Prakash Turant Bhaga. Okay, so it's like V Bhaga, not B, V Bhaga, right? So Satya Prakash Turant Bhaga. So you can get the SPTV from here. What are those terms? You know it very well. You studied the whole thermodynamics. It's your entropy, your pressure, your temperature, and your volume. Now coming on to the terms which are given in the middle part, which are HGUA, you can just learn them in a way which is Hey God Ow. So it's like AU, okay? Hey God Ow, and these are for in between squares. Now you also know that what is HGA and U. So H is enthalpy, and your G is Gibbs free energy. A is your state function. So now talking about A, so we have not seen this state function in a whole discussion, and hopefully this will be not asked in your exam, but still it's a part of the, you could say, the Maxwell equation, so I'm giving it, right? And lastly we have the U, which is internal energy. So let us move on to the trick part. Okay, so how do we derive the different relations from the square? Let us move on to that. The first and the most basic relations are related to the S, P, T, V, H, G, A, U, R. So you will derive this enthalpy, the Gibbs free energy, the A, and your internal energy in certain functions. Okay, so there are 4 functions for each of them in terms of the functions which are given in the corner. Now how do we derive it? It's very simple. If you look at the magic square here, then what you can notice, let us talk about internal energy, say. So you can see there is internal energy in the green box. How do we derive a relation with the internal energy? So write internal energy as du. Okay, so we are justifying it for a small change, so we write it for as du. Now next what we do, you can see on the either side of the internal energy we have S and V, which is entropy and volume. How do we write this? We simply take the derivative, so you can write it as du is equals to ds dv. Now we are not implying any algebraic operation between them. Okay, so we are to go on to that part. Now we are just forming the main equation. There is no logical reasoning in it. It is just a mnemonic to learn it, right? Okay, so now we have got our derivative. Our next part is, look at the arrow here. Where is S going? You can see the S is going on to the T and the V is going on to the P. They are linked to each other by this adjacent lines, or you can say the diagonals. So what you can say, if you are talking about ds, which is written as here, you can multiply it with the diagonal term, which is T, temperature. Okay, so we got the TDS. Similarly, for the dV, we multiplied with the pressure, because pressure is on the diagonal term. Now we got this form. Okay, so first we have du, we are talking about the middle term. You can derive it similarly for the enthalpy, Gibbs free energy, and the A. So I am leaving this part on to you. We will see the final relation, but you need to do the same thing, the same process that I am doing it here. Okay, so first we started with du, then on the either side of the u we have s and v, so we took their derivative. After that, uh, the inotropy, which is S, has a diagonal element as T, which is temperature, so we multiply ds with T. Similarly, the volume has a differential dV and its diagonal element is P, so we multiplied with P. Okay, not the derivative, the simple P. Now next what we do, the next thing is to decide the signs between them. Now the sign that you will assign will be plus for head. So if it is a head, you will give a plus. If it is a tail, you will give a minus. How? So suppose if you look at a temperature, then it is a part of the head, right? So you can see that the arrow is going and the head part is aligning along with the temperature. So you will give it a positive sign. Whereas if you look at P, then the P is having the tail. Now which element you are looking? You are looking at the diagonal term. Which element? The diagonal term to assign the sign. So the diagonal term, again I am repeating it, the diagonal term is temperature. It is having a head part, so it will have a positive sign, right? You can see the head part is given a positive sign, and then we have the P, which is pressure. So it is having a negative sign because it has a tail aligned to it. Now final equation that we got is du is equals to plus TdS minus PdV. Now this is only for the U. Can we derive similarly for the enthalpy, Gibbs free energy, and A? Yes, we can do it. It's very simple. Just follow the steps for each of the state functions. So let's see what is the result that we got. Now I'm giving you some time. Just think about it, right? So what are the functions that you can derive? You can derive it very quickly. Just write down in your notebook. Okay. So I am counting it till 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so your time is up. Now let us look at the say our final derivations that we got from this trick. Okay, so this was our magic square. So here it is again. Now we are not coloring it because it is not for a specific state function, but it is for all. We got it for du. It was TdS minus PdV. We dropped the positive sign because it is already there according to the convention. Now what about the next function? Let's talk about dH. So if you take the H, which is enthalpy, you can see that on the either side we have the S and P, which is entropy and the pressure. So you took the derivative. See, we have the derivative of ds and we have the derivative of dP. Okay, sorry, the derivative of entropy and the derivative of pressure. Now what are the diagonal terms to the entropy and pressure? For the entropy, we have the temperature. So we have written the T with ds. What about the pressure? So pressure has a diagonal term as V. So we have written volume here. Moving on to the signs, which is the last part. Since V and T both are aligned with the what? With the head. So both will get a positive sign. So we got the final equation as dH is equals to TdS plus VdP. Now moving on to the next function, which is related to the Gibbs free energy. So how do we write it? Very simple. Again, follow the same instructions. First write dg, which is your center part. Then on the either side we have the pressure and temperature. So we took the differential of that. So dp and dt. Now if you look on the diagonal term for pressure, it is V. So we write it as VdP. And for temperature it is S. So we write it as SdT. What about the sign? So volume, which is V, is getting a head. So we will put a positive sign. And the entropy is getting a tail. So we'll put a negative sign here. And that is how we get our equation for the Gibbs free energy change. What is the last equation? It is related to dA. Okay. So how do we define it for dA? Very simple. Again, we take the V and T, which are present on the either side, as differential. We multiply it with the diagonal term to give us PdV and SdT. Then both S and P are on the tail side. You can look at it's very clear. So they both will get a negative sign. So these are the four equations that we got it for internal energy, enthalpy, Gibbs free energy, and A. Now we will just modify it a bit to get our new results. So those results are also very, very important. Let us look on to that. If I talk about the first modification we will do upon du. So we have the equation du equal to TdS minus PdV. What we do is we take the volume constant. If we take the volume constant in this equation, you can say it very clearly that this dV, which is change in volume, will become 0 because volume is constant. So the change in volume will be 0. Therefore, this whole term PdV will be equals to 0. What you can write now? Du equal to TdS. Now cross multiplies this ds here and take it as volume. Now you would ask, so is it a good method to do? Yes, this is probably good for finding the answer quickly. But what is the thing that is actually done here? So we are differentiating this whole thing with respect to entropy while keeping the pressure constant. So du by ds at constant V, okay, so this will give you the first term. Then Tds by ds at constant V. So T is not changing, so we'll take it as constant. So ds by means I would say the differentiation of or the change of entropy with respect to S will be 1, right? So ds by ds will be equals to 1. After that, if you move on to minus PdV, then dV by ds at constant V. So you're differentiating the volume with respect to entropy at constant volume. So what will be the change? Of course it will be 0. So this term whole will be doomed to 0 and you will get your final equation as du by ds at constant V is equals to T. Now we will apply the logic onto the next equation. We will not go through this differentiation part. I would suggest you to do the differentiation by your own one more time. Okay. Now what can be the next relation? You can keep the what? You can keep the inentropy constant in the next case. So see, we have taken the inentropy constant and whatever is written here, you take it in the denominator of the du. So du by dv at constant S gives you minus P. So you have to retain this negative sign. So this is obvious. Moving on to the next thing. Next thing is related to the enthalpy. Now in the enthalpy, we can take similarly two equations. What are those two equations? First, we'll take the pressure constant that will give you VdP as 0 and therefore dH by ds at constant P is equals to T. In the next part, if you see, we have taken the entropy as 0. So it will give you dH by dP at constant entropy is equals to volume. Moving on to the Gibbs free energy, what can we do? We can again take your pressure constant. Okay, so in this case, we are taking this pressure constant. So this will give you dG by dt at constant P, which is pressure, is equals to minus S. Of course, this minus sign will be retained. Then in the next part, we are taking the temperature constant. It will give you dG by dP at constant T is equals to V. Moving on to the last one, which is A. So how we can write dA in different terms? So it's very easy. dA by dt at constant V. So we are keeping this volume constant. So minus PdV will be equals to 0. So that will give you minus S. Okay. Similarly, if you take the temperature constant, then this dA by dV will give you minus P at constant temperature. So these are the four equations that we got. Now, can you see equalities here? Yes, we can clearly notice these equalities. What are those equalities? You can see that du by ds at constant V and dH by ds at constant P is equals to temperature. So you can equate du by ds at constant V and dH by ds at constant P. Similarly, if you look on the pressure part, you will see that du by dV at constant S is equals to dA by dV at constant T. Now, in this sense, you can derive various equations. We have two more terms which is related to volume and negative entropy. So volume is dH by dP at constant S and that will be equals to dG by dP at constant T. Similarly, for your minus S, you will have dG by dt at constant P is equals to dA by dt at constant P. Finally, we can write all of these relations in one part. So here is your conclusion of that. So first was related to temperature. So it will be change in internal energy with respect to entropy at constant volume is equals to change in enthalpy at constant entropy at constant pressure. So that is equals to temperature. Second is related to minus P, which is change in internal energy at constant entropy with respect to volume, and change in A with respect to volume at constant T is equals to minus P. Moving on to the next, which is minus S. Again, change in Gibbs free energy at constant pressure with respect to temperature, and change in A with respect to temperature at constant V. And lastly, we have this volume, which is change in enthalpy with respect to pressure at constant entropy, and change in Gibbs free energy at constant pressure with respect to temperature. So these are your 4 equations. So we are moving on further. So we already have, I guess, 8 equations in total. So this 4 and the previous 4. The middle one that you saw, which was a modification. So this was just a process to gain this final equations. The next is the relation that is related to SPVNT. So there is a very short mnemonic for it. How do we write it? So it's very simple. So there are certain conditions that you should remember. So first is that PV should be equals to ST. So this is the first condition. You will get it. What is the meaning of this? Second thing, if you are seeing a S by P or a P by S, you will give a negative sign. So let us look on to a specific equation in this way. So in the first part, what we are doing, we are cross multiplying this PV and ST. So this will give you P and S and T by V. It's very simple. You can cross multiply it and you will get it. Now you will take the differential of this. What we will get? dt by dv is equals to dp by ds. Okay, we have just written this equation in the form of differential. Now the next part is taking constant. So what are the things that we take constant? It's very simple. What is present in the denominator on the either side will be taken as constant. You can see that on the right hand side, the entropy is in the denominator. So you will take on the left hand side entropy as constant. So dt by dv at constant s. If you took for the right hand side, then you can see that the volume on the left hand side is in the denominator. So you take dv at ds at constant volume. So it's very simple. You just have to take the opposite side denominator as the constant for the corresponding one. So this is your third thing. And the final thing is putting the sign. You have already seen it. If you are taking a P by S and a S by P, you will surely take it as negative. You can clearly see that we have a P by S condition here. If it is a P by S, we will give a negative sign. So that will give you your final equation, which is minus dp by ds at constant v. So we took this sign as negative. No, this is not a final equation, of course. So we took this sign as negative because we have a P by S term here in the differential part. Now we can write the final equation as dt by dv at constant s, that same previous equation, along with a negative sign against the dp. Now in this way, you can derive various equations. You can just rearrange this PV is equals to ST, and in each case you should get that PV is equals to ST. So this is the basic requirement. So let us look on to the equations that we can get in the similar way. You can see if you cross multiply it, ST PV, okay, you will get the PV is equals to ST. Next thing you can notice that we have the constant which is present on the either side as the denominator. So S is here the denominator on the right hand side, so we take S as the constant on the left hand side. Similarly, on the left hand side, volume is present in the denominator, so we take volume as the constant on the right hand side. Next thing you have to consider about the sign. If you see a P by S or S by P, you take it as negative. So you have a P by S term, you took it as negative. Similarly, you can derive various equations. In this case also, if you cross multiply the differentials, you will get it as PV is equals to ST, and there is no doubt in it. Next part is taking the constant. Again, we can see that S is present on the denominator on the right hand side. So we take S as constant on the left hand side, and the right hand side we can take the pressure constant. Now, is there a S by P or a P by S term? Absolutely not. S and P are present on the opposite side, so there will be no negative sign. Our next one is S by P again. So we keep putting a negative, we are putting a negative sign here. Again, if you cross multiply it, you will get PV is equals to ST, and the constants are the denominator on the right hand side for the left side, and for the left side, right side, we have the left hand side denominator. Okay, I guess this part is clear to you. You can try it similarly for the last equation, 4 number. And this is your third set of relation. So it's very easy to derive this trick. Just try it by yourself in your notebook. If you'll try it 2 to 3 times, you will get the part that what is happening in this whole situation. Now moving on to the next, which is conditions for spontaneity. Again, we will take the case of your Maxwell square for that. So how do we take it? Suppose we have this Maxwell square. So we will first define the spontaneity with respect to the variables that are present on the corner. So what are the variables that are present in the corner? So we have inotropy, pressure, temperature, and volume. So first let us take it for the inotropy. How do we define it? So if you are taking the inotropy as the varying function with respect to spontaneity, then we will write S as ds, taking the differential. In the next part, we will take the adjacent parameter as constant. You can see on the right hand side of the inotropy, we have H and P. So we will take the enthalpy and pressure as constant. What we can write? We can write it for U and V also, because U and V are also present on the adjacent side. Now, there are two sets that can be possible. First with respect to U and V, and second with respect to H and P. Let us consider it for the U and V. So how do we write it? So we have ds at the s at the corner. We will take the differential, or the adjacent side we have U and V. So we take internal energy and volume as constant, and the corner term should be greater than 0. So there are two terms with respect to which we can take inotropy, which we can take spontaneity. First are the corner terms, and second are the middle terms. So with respect to the corner term, we always put it as greater than or equals to 0. Okay. So we have taken the adjacent variables, which is U and V, and with respect to keeping them as constant and differentiating with S, we are getting it as greater than 0. So this is the first criteria that we get it for the spontaneity. Similarly, we can do it for the H and P. So how we can write it? If you take the H and P at constant, so we can write change in inotropy at constant enthalpy and pressure must be greater than 0 or equals to 0 for a spontaneous process. Is it clear to you? If you are getting it for this part, which is inotropy, you can similarly define it for pressure, temperature, and volume. So let us look at those equations that we will get upon keeping the pressure, temperature, and volume constant. So functions at the corner can be written as dp by dp at constant g and t. So change in pressure at constant g and t should be greater than or equals to 0. You can go back to the thermodynamic equation and look on to this, how we are getting it. So if you take about the pressure, so first adjacent term is Gibbs free energy and temperature, and the second adjacent term are enthalpy and entropy. Okay, so we'll take both the cases, and in both the cases, the change in pressure should be greater than or equals to 0. What can be said for temperature? We have two terms A and V on the adjacent side, and the second set of two terms is Gibbs free energy and pressure. So this will be again greater than or equals to 0. Last, we have the volume. So which has the first set of two terms as A and T, and it should be greater than 0 or equals to 0. And the second set of two terms is S and V, which should be again greater than or equals to 0. So these are the equations that you can get for the corner term. So for each corner term, you are getting two situations for both adjacent two set of terms. Now we can move on to the middle term. Opposite to the middle term, what we do, we take with respect for the middle term, I am saying it, we take it with respect to the variables which are present on the either side. So for suppose we are considering for U, so we have S and V. So we take S and V as constant, and rather than keeping it greater than 0, if we take it for the internal energy and we are writing it as du with respect to inotropy and volume, then we take it as less than 0. Okay, it will be less than 0. So the change in internal energy at constant inotropy and volume should be less than or equals to 0 for a spontaneous process. So this is the way we say the complete sentence. Again, I am repeating it. Suppose we are writing it for internal energy, then it is said that the change in internal energy with respect to inotropy and volume should be less than or equals to 0 for a spontaneous process. Moving on to the next thing, what can be the next term? We can take enthalpy, Gibbs free energy, and A. So let us write it for each of this. So first, let us give it for enthalpy. So on the either side for enthalpy, we have inotropy and pressure. So the enthalpy change should be less than or equals to 0 at constant inotropy and pressure. Then the next term is with respect to A. So the change in A at constant temperature and volume should be less than or equals to 0. And the last term that we can look upon is Gibbs free energy. And we know this equation already. So dg at constant T and P should be less than or equals to 0. So this is the final derivation that we got. How many sets do we get for the Maxwell equation? If you just realize it, then from the first part, if I start, then from the magic square, we have 4 sets. And from those 4 sets, we have again the next 4 subsets, right? Coming on to the PV and ST, we have again 4 situations. And lastly, for the case of spontaneity, if you look, then we have 12 situations. So total, if you count, it is 12 plus 4, 16, 16 plus 4, 20, and 20 plus 4, 24. So you can just derive this 24 relations simply with the help of Maxwell equations. Okay, so I hope you got the point. If you got this, so here is a small question for you. It's very easy. So you have to see that which of these relations are correct. So there can be multiple options that can be correct. You can easily see that it is written along with this bracket, right? So your time to solve this question starts now. You have some time to solve it. It's very easy. Just follow the PV is equals to ST part. You will get the relation. Okay, your time is up. Let's see how we can get it. So if you look at the Maxwell square, what we can remember, so we don't need the Maxwell square. Okay, sorry, we don't need the Maxwell square here. We just need the PV is equals to ST. So this was the first condition. Then second, if you see S by P or P by S, you take it as negative, and you can move on to the relation. For the first case, we are taking the T by P and V by S. So this is the situation which is possible. We take the differential of that. Now, on the right hand side, whatever is the denominator, we take it as constant for the left hand side, and the vice versa is taken for the right hand side. If you do so, you will get it as dt by dp at constant s is equals to dv by ds at constant p. Now, is there a negative term here? No, we don't have s by p or p by s situation. So this is your final equation. This is the first thing that we can, this is the first equation that is correct. Moving on to the next one. Let us assign the T by P as positive. Okay, so again, this will be positive. It's very true. We don't have to worry about it. It's obvious. And V by S will be also a positive one. So therefore, we'll get your final equation as dt by dp at constant entropy is equals to change in volume with respect to entropy at constant volume. Right? So this is the answer. So in this way, B and C both are correct. So this was all for today's lecture. I hope you enjoyed it. Thank you for attending the session.